Thank you for coming to the lecture. I will talk about my PhD research today. The name is Toward the Quantum Theory of Cognition, History, Development, and Perspectives. My name is Tomas Veloz. I'm a PhD student at the Department of Mathematics in Interdisciplinary Studies, actually, at the University of British Columbia, Okanagan. But I also have affiliations with the Centro Leo Apostel, this place, and the Institute of Philosophy and Complexity Sciences in Chile. That's the Spanish name of the institute. So we'll start. As a salutation, or like first thing to say, I'm gonna talk around this concept that is called conditions of possible experience. So the conditions of possible experience were defined by George Boole in the beginning of the program of Foundations of Probability, when this was just started to be defined. And the conditions of possible experience indicate that data might have be observed or cannot be the result of an actual observation. So the conditions of possible experience are a very deep concept that relates that relates reality to our observations, basically. And it was developed in the context of probability, with deck cards or dices. So what type of outcomes you can observe in a certain experimental setup. So this is, and I'm gonna connect this to cognition and like some other things. So the topic is foundations of science, but applied to cognition. So it's foundations of cognitive science, but it applies to science in general, of course. And it's related to my PhD in interdisciplinary studies, whose topic is quantum cognition. And for reasons of space, some references will be numbered and some other references will be shown with names and years. So if you want to get those references, just let me know. So the outline, it's going to be, I'm going to review the classical notions of experience, those that come from the tradition of Boole, and then I will analyze these conditions in the context of cognition. And then I will introduce quantum cognition, because of course the idea is that the classical conditions of possible experience are usually violated in cognitive experiences, or the way we think about our experiences. And then I will go a little bit further, introducing some new notions of experience in this context. Okay, so let's go with the notion of possible experience. As I said in the beginning, this was introduced in his investigations of laws of thought. That's the research program. What are the laws of thought? And so the idea is that a possible experience constrains the relative frequencies, which are supposed to imply probabilities, of an observational procedure. So it sounds very abstract, but it's actually very simple. I can give, for example, the typical probabilistic framework. Consider an urn with 100 balls and 2 experiments. I take a ball and it's red, and then second I take a ball and it's wooden. These are 2 experiments I can apply to the balls in the urn. And then I define these outcomes, yes or no. Like I take the ball and I see if it's red or if it's wooden, and I say yes or no. So these are constraints that must be satisfied by the experimental procedure. AB means I apply the 2 experiments. So I take the ball and I check if it's red and wooden. So red and wooden balls have to be in a smaller amount than red balls, and red and wooden balls have to be in a smaller amount than wooden balls as well. You cannot have more red and wooden balls than red balls. That's basically the point. And there is another constraint which says that the number of red plus wooden minus the number of red and wooden cannot be smaller. It has to be smaller than 1. It cannot be larger than 1. So mu represents the probability of an outcome, or its approximated relative frequency, and AB, as I said, is the joint experiment. So I'm just going to give a little example. If you measure your relative frequencies, you perform lots of experiments here with your urn, maybe more than 100 balls, maybe thousands of balls, and once you apply your experiment, you find out that the probability to extract a red ball is 0.7, the probability to extract a wooden ball is 0.42, and the probability to extract a red and wooden ball is 0.1. This is not a possible experience. If you look at the numbers, it doesn't seem like really immediately, it's not trivial that this is not a possible experience. But the fact is that 0.7 plus 0.42 is 1.02, and then by this inequality you find out that the conditions of possible experience here are violated. Basically, this is saying that there are balls, because you have red 0.7 and wooden 0.42, then this constraint red and wooden at least 0.12. So you cannot have 0.1, less than 0.12, because you have too many. It's already like the single experiment's constraint to match the joint experiment. That's basically. Do you follow more from till here the idea of possible experience? So going more in a mathematical perspective, the conditions of possible experience imply the existence of a classical probabilistic representation, where classical probabilistic representation means what was axiomatized by Kolmogorov, basically. It is in probability, this is well known, it's an axiomatization. And these conditions of possible experience is important to say that are always satisfied if experiments can be performed on a single sample. If they are performed on a single sample, of course, these conditions are going to hold. So if you have an urn, then these conditions will never fail because you have your single sample. But the thing, I'm not going to go yet to how these conditions can be violated, but I will just make a small mathematical interlude here and say that the conditions of possible experience can be deduced for as a logical system in terms of just logical conditions for any number of experiments having any number of outcomes. And this has been done in many ways by the correlation polytopes of Pitofsky or probabilistic logic, or linear programming, category theory. There are lots of approaches, so it is from a mathematical perspective, it's a very interesting question and an area of investigation. There are mathematical interests such as the representation of these conditions, the satisfiability of these conditions, what types of bounds you can find for these probabilities, how to optimize certain process if you know what are the conditions. The methods interestingly combine logic, probability, geometry, and symmetries, algebra, many other things. So it's a very deep mathematical question and also philosophical question. So it's interesting from a scientific perspective at least. So we can say that these conditions bridge logic, probability, and experimentation. So it's a bridge between what we think, what we can represent, and what actually happened, at a very deep level. And that also, for that reason, entail the foundations of many cognitive theories. So you can connect these to expert systems, which this guy's expert system is decision making under certain conditions. So then you apply these conditions of possible experience and say, okay, according to the information I have, this is what I can deduce, so this is going to be my decision or my suggestion. In traditional artificial intelligence, this is done by classical logic, most of the cases. You can extend this to fuzzy set theory and possibility theory and apply it to categorization, which is done in many cases for engineers generally, using these decision-making frameworks like Dempster-Schaffer theory. I don't know if anybody knows of this, or applied to decision theories in economics. The principle of utility maximization and all that, normally it's applied by using probabilistic frameworks and using the information you have to maximize. So you always, these conditions of possible experience are always underlying these theories. The same with Bayesian models, which are classical probabilistic frameworks in modern artificial intelligence, or the consistency of databases in computer science or like big data kind of thing. So these conditions of possible experience happen across multiple areas in cognitive science and artificial intelligence. Is at the core of it a big bold, etc. Because anywhere you find, you will apply.
The condition of possible experience is that, do you mean that inequality?
Yeah.
So
basically, yeah.
So
At the deep level is that certain constraints, there are certain basic constraints concerning what can happen in a certain system. And these constraints are described by the conditions of possible experience in terms of inequalities. But there are many other representations. As I said, you can do it with geometry as well. Instead of like inequalities, you find polytopes, and then points of this in this space will be events or will be probabilities. So, or you can use algebraic representations with symmetries, or like.
But these are all equivalent.
Or equivalent. Mathematically, they are all equivalent. Well, it took a while to prove that, but yeah. Or you can use Cartesian vectorial representations. Or database in general. There are many different ways to represent this. So that's the point I want to make here, is that the conditions of possible experience are not a set of inequalities, are a whole characterization of, depending on the language you use, what can happen. So of course you can use the polytope like or even with satisfiability conditions are in terms of logic, like three-sat kind of sentences.
But there are not more conditions than the ones you showed in
no, yeah. At the end they are all equivalent, but what they mean. I'm more pointing to what they mean rather than how they look. That's the idea, like the context I want to bring for the rest of the lecture. So now I'm going to present a very typical and well-known experiment in psychology, which is known as the Goldfish Effect. So I tell you, think of a typical exemplar of pet, and normally most of the people will think of something like this. This is normally what we think of a pet. And then you say, think of a fish, and many people, or most people, this is the experimental data, they come up with an idea like this about a fish. And then you say, think of a typical pet and fish, and what normally people come up is something like that. Pet and fish is called guppy. Okay, so then
goldfish actually, but
goldfish, yeah, goldfish. So this is a goldfish. Yeah, that's funny. I don't know about fishes, but guppy on goldfish, it could be called the Goldfish Effect, because I've seen the data tables, and guppy and goldfish both follow the same. It's just that guppy maybe is one shorter word. Yeah. Yeah. So the thing is that guppy is a typical pet and fish, but it's not a typical pet, neither a typical fish. So how come is, if we recall, I'm just gonna I can come back to this if you want to see, but formally, if you have a universal set of exemplars of certain concept, certain category, as we said, and you want to model the typicality of these exemplars as a certain function, as in the same way we did before, saying how many balls, you can retrieve the probability of that an exemplar is a guppy, the probability that an exemplar of a certain category is a cat or a dog. So you can think that categories are somehow urns, and the exemplar of these categories are balls in these urns, and the probability to extract one of these is analogous to what we were doing. So the idea is, can we think about categories as if they were urns with balls, and about the reasoning process of extracting a ball from this urn? Because this is what people do in probability. Probabilistic approaches to cognition assume that categories are somehow urns, and that the reasoning about these categories is somehow extracting balls from the urn, because that's what probability theory was
biased
developed.
When you ask people to extract an example from a category, it's a very biased. In an urn, you don't know which ball it is.
Yeah.
But if, for example, suppose that there would be smaller and bigger balls, there would be a bias to pick out the bigger ball, and if all the bigger balls would be red,
or you can put more balls of one type, of less balls on the other type. This will correlate with the size. It's
it's not so much a distribution of elements in the category, but the fact that you're biased to pick out particular elements of the category.
Yeah.
If you ask for typicality, you're not going to get as a typical fish an anchovy or a swordfish or.
Mm-hmm. Yeah, so that's the idea, to try to connect this type of experiment to the type of theory that is applied to represent this, and see if the conditions of possible experience hold for this type of experiment. And of course, as I was saying, like the conditions, these conditions from any logical perspective will imply that this type of constraint apply. So the typicality of pet and fish has to be smaller than the typicality of pet, and the typicality of pet and fish has to be smaller than the typicality of fish. And of course,
typicality is not the same as probability.
yeah, no, it's not the same. But you can apply with it. And I'm making this experiment, but this has been tested with other, like membership, which is much more close to. I will show later another example. And also with the probability itself, like the Linda experiment, you know, in Tversky and Kahneman experiment, they estimate the probability, the likelihood of the following events. They do it right, like, and there is a lot of research and many other experiments where they explain people what probability is, and then they rate, and still these conditions are violated. So, but I'm going to talk about that maybe later. So psychological findings show strong overextensions. This is called overextensions. So inversions of these relations in experimental data. So this contradicts logical notions about concept combination or experiments concerning categories, combinations of categories, and illustrate their non-compositional character. Non-compositionality or compositionality is rooted in probability, because the axioms of probability say that when you take two events, the probability of these two events is going to be the sum of the probabilities. And then there is a formula that relates to this. And non-compositionality is when you cannot connect the two events together, are not represented as a mere combination of the events, but you need something else that can subtract or add certain features. So yeah, I'm going to go over that later as well. But the idea is that there is a little simple evidence to show that the conditions of possible experience are at least questionable from a cognitive perspective. So I'm going to talk a little bit now about this Itamar Podolski's reconsiderations of probability and possible experience. This scholar did a very interesting philosophical studies in the foundations of probability, classical and quantum probability, and try to relate why these things are in a way so weird. So he proposed that an interpretation for quantum physics requires a better understanding of the notion of probability, and that was the entire research program. So it's important to remark that if we cannot measure on a single sample, if we cannot perform measurements on a single sample, then it's when the conditions can fail. And what are the possible reasons for this? This is an interesting set of possibilities. Failure of randomness. The first is still, even if you have a single sample, you can have detector problems, and that is going to be why you fail on the conditions, because your detector is not good, so it biases the sample, the detector itself biases the sample. This can be taken a little bit more deep when the measurement performs changes on your sample without your request, or you are not aware that your measurement is actually biasing your sample. And this is called incompatible measurements, and it is related, it's to the observer effect in quantum physics. If you don't know about that, don't worry, it's not that important. There is a more interesting philosophical condition or possibility. There is no distribution. Certain things we measure just don't have any distribution, and this means that we have to give up causality. From a philosophical standpoint, we can give up causality and say, well, things can be as weird as you want, because there is no need to accomplish any law of nature. There are certain things that just don't have any law, and that's all. And that's another philosophical standpoint towards cognition. You will never be able to mathematize these things because they don't follow any rule, and that's it. It's an interesting standpoint.
So you cannot have a prior also to a population of events like this. You cannot have a prior. You cannot make any assumptions what you will get.
Eventually, well, that's a standpoint. Yeah, that's what I'm trying to say. That you can say, oh no, this is because we have measurement biases. We will never measure the mind of a person because this is too hard, because we change the mind of a person when we measure. That's another explanation of measurement bias. Or another is like, well, we never take a right sample, failure of randomness. We always take a sample from a certain culture, from a certain, so we cannot study cognition anyways, because we will never get like a fair sample to really understand what's going on. But there is a fourth option that I suggest here for reflection, which is called mathematical oddities. If you still have a probabilistic representation, you might have, for those that know, non-Lebesgue measurable events that can have probability 0 or 1, depending on how do you consider your integral, basically. So if you study, for example, fractal events in a probability space, fractal events, because they are so weird, mathematically weird, they can have multiple probabilities associated to them. And that's a very interesting line of research that I haven't explored, and I know nobody has done it as far as I know. But I think it's very interesting, and it's an alternative, completely alternative to what I'm going to present now, because I'm going to go more or less in this line in quantum physics. It's proposing that quantum physics is a better framework, but this framework, it's also interesting. Let's just leave it here.
It is something that Podolski started to develop, I think, in his book. I read something about
yeah,
it.
he put some, he have done some, he have give some first steps, like some impulse to start to do it, but he haven't come up with a theory or like a proper interesting examples, and even less just data. He never collect, as far as I know, he hasn't collect data at all, just like thought examples.
I think he died.
Yeah, unfortunately he died pretty young, I know.
This is completely
Yeah, it's the same as Tversky, another guy that Tversky and Podolski are guys very important for this research, and they both died very young age, so it's very sad. Yeah. Anyways, the notion of possible experience depends on the structural properties of the observation process. So when you apply like the Boole conditions, Boole is giving you a very strict and very clear observational process that is inspired in balls and on urns, basically, or cards on decks or dices that are being thrown. So from all this, I'm going to explain why we can propose that the features of quantum measurements and in general quantum theory can be applied in cognitive phenomena as a representational framework for cognitive phenomena. So now I'm going to give a little bit of explanation of what quantum cognition is from as a historical introduction. Quantum cognition is an area of research that dedicates to identify quantum structure and develop quantum-like modeling in domains such as cognitive science, economics, artificial intelligence, etc. So what do I mean when I say quantum structure? What is this identification of quantum structures? Well, you find that certain phenomenon can be explained in terms of incompatible measurements, as I was saying before, measurement biases of observer effect, or that for certain phenomenon you might find that state superposition and interference are interesting representational tools. You can find entanglement on certain measurements or certain entities, and many other things. I will show some examples. And what do we mean by quantum models? Well, they have been applied to categorization. So pet or fish can be represented as quantum particles, basically, and the state of a quantum particle is this vector, and then you apply the whole mathematical framework of quantum physics to reproduce the psychological measurement of typicality or membership or representativeness or many other called semantic estimations I will mention later. On decision making as well, you are confronted with a certain situation, like on a paper you read and say, well, this is your state, these are things that are happening to you, and these are the options you can follow. What option you will follow? Again, the same. This state of mind is represented as a quantum state, and the measurements doing this, deciding this or deciding that, is going to be the outcome of a certain measurement operator in the same way that quantum mechanics does. For information retrieval as well, the same. You have the web or a certain collection of web pages represented in a quantum state, and then you have a certain query, a certain question that represents a certain measurement operator, and this gives you a collapse, and then this collapse state after measurement will represent the possible documents that you will be that will be relevant for your query.
Well,
And
actually, I think
etc.
that is being used because as a similarity measurement between documents, you can use the cosine of the
Yeah.
angle between the vectors, which
Mhm.
is equivalent to the probability of collapse.
It has been applied, and it has been actually proposed by some people in Italy and in Poland. They have developed this for like 5-10 years. Unfortunately, I don't know very well what they do. I know they haven't applied this, I have read the papers, but they have come up with some negative results that I'm not so sure they apply. For example, they have proven or suggest, like they say they have proven that complex numbers are not necessary, or they don't bring any new interesting thing.
Yeah,
And
I don't think there's
in
much
our
use,
group, we
complex
claim
numbers.
that complex numbers are really like an advancement from a representation point of view. So it's a big area. People say different things, and you cannot be aware of what everybody does, neither agree with what everybody does. So, but I know this has been applied. So quantum interaction is the sort of umbrella of quantum cognition, because quantum interaction does not just apply this to cognitive system, but also to biological system or chemical systems. So, but important to say is that it does not take any position with respect to the quantum brain hypothesis, which is like the work of Penrose and other guys that have proposed that cognition is in a way the result of quantum processes occurring in the brain. This is just representation. Quantum physics representing cognitive phenomena. It's not saying, well, there are neural impulses and so on, and quantum is there. Nothing of that. So it's in a way architecture independent. This can be the outcome of a computational algorithm or a human brain or a mechanical process. It doesn't matter. It's not related to the brain. Okay, so I'm gonna give a little example of data in the sense of pet fish example. So consider the concept furniture, household appliances, and their conjunction furniture and household appliances. This is another example. People estimate the typicality of objects like ashtray, vacuum cleaner, coffee table with respect to furniture, household appliances, and their conjunction. And this is how the data looks. So I don't put the one and the other, I just put minimum and maximum. So for every exemplar, you have the minimum curve. So minimum between A and B, it's going to be always the minimum. Maximum
The minimum of what?
Minimum between mu A, minimum between mu A and mu B. So minimum between the typicality of the exemplar with respect to furniture compared to the typicality of the exemplar for the concept household appliances. You take the minimum and put it here. Then you take the maximum and plot it there. So because these curves crosses, for certain objects the minimum is household appliances, and for others the minimum is furniture. So if I will plot the actual curves, this will look like a mess. This will look all crossing. You see what I mean? So I just plot the minimum and maximum so you can see the bounds. Because, as I said, the conditions of possible experience request that the combination curve has to be below the minimum of both, because you requested that is, if you remember, you cannot be red and wooden more than red. So you have to be below the minimum. You see what I mean? So that's what why I plot the minimum curve here.
Mm-hmm.
So we would expect from a classical condition of possible experience, or from a classical probabilistic perspective, that the combination curve, which is here, should go below the minimum. But it actually goes above the minimum, sometimes even goes above the maximum. So you are more of a combination than you are for the former elements in the combination. You are more red and wooden than red or wooden separately. So you are more a pet and fish than a pet or than a fish. You see, this is called double overextension, and it's something that is in many cases is very hard to model, and it of course goes beyond what any fuzzy probabilistic theory could give. Because there is a formal argument to explain that. I won't say that. But what it is interesting, I just want to remark this, is that I took also the average between the minimum and the maximum, between the both probabilities, furniture and household appliance, and then you look at the maximum and compare it with the combination, and you find that the average actually gives a much better estimator for the combination than the minimum or the maximum or any other curve. I made this statistical analysis, and you find that the average is a pretty good estimator. It doesn't fit the curve, because in many cases, as you see, you go down or you go up too much, but correlation wise it's pretty much a good estimator.
But it's not intuitive to interpret the average as something that we understand, because it's the average between furniture and household appliances, something like this.
From a classical perspective it's not, but from a quantum perspective it's direct.
Okay.
I will show why. Unfortunately, I'm not going to present the quantum model to the full extent, because the audience is not so mathematical, but I can give more details later. I will still show the formula, and we can go 2 minutes to analyze the full formula, which is very complicated, but we can analyze just one term. So when quantum meets cognitive data, this is, as I show one example. Now I'm going to tell you more examples, but I won't elaborate on this. Conjunctions of concepts, disjunctions of concepts. This has been done by Aert, Soso, Gabora, and a little bit of me during the last 10 years. Borderline contradiction. This means I am happy and not happy. You know, from a logical perspective, you cannot be happy and not happy. But we humans normally handle this type of propositions very well. We can talk and understand. We are not gonna freak out if someone says, well, I feel like I'm hungry but not so hungry, and not so hungry. Or not hungry, just hungry and not hungry, or rich and not rich. This is completely easy to handle for us, but if you put this sentence in a machine, you get a blue screen, basically, you know? So why we don't freak out with this type of sentences, but computers do, is because in a certain way the conditions of possible experience developed by Boole, that's the argument I'm trying to put, are not holding in cognition. That's the point. And this was studied by Sandro Soso, and he again find out like a quantum model that represents very well the data and blah blah blah. Conjunction fallacy, we discussed this the other day. You know, it's a similar overextension, so I won't elaborate much on that, but this is pretty popular, and it's actually what is giving rise to quantum cognition to become popular, because it's in the media now, in like physics.org, and many popular like Wired kind of magazines are publishing about this type of result, because the conjunction fallacy is part of a research program that led to a Nobel Prize, basically. So that's why analyzing this problem from a quantum perspective, it's becoming popular. Order effects, the same group, order effects. So if I present the questions in reverse order, I give completely different responses. So measurement biases, it's analogous to the measurement biases. Paradoxes in decision making, Ellsberg and Machina paradox. These are related to the problem that people have to handle uncertainty. So we are much happier to make decisions when we know what's going to happen than when we don't know what's going to happen. Even when what's going to happen doesn't matter really for our decision, we still feel a certain problem to make a decision. So this Ellsberg,
that was the example of the people who are asked to go on vacation.
Yeah.
And they don't know whether they succeed in the exam or not.
Yeah, I will give a very short example. Like it's an analogous example called the Ellsberg paradox. So you are considering to buy a property, a piece of land somewhere, and elections are coming. Okay, so it can win the right or left party. So you analyze the case and say, okay, if the right party wins, I think I should buy the land. And then you analyze the case, if the left party wins, I think I should buy the land. But if you don't know who's going to win, then you won't buy the land. You know? So you are considering, and this is tested experimentally, basically that's what happened. You can put variables to people that bring uncertainty, but this uncertainty is not relevant for the decision, and still people will like step back to make the decision.
But I think it's a general problem also with this thought experiment, is that in the back of our mind, consciously or unconsciously, we know that other things could happen. There could be a break from the army destroying the government because it's the elections. I mean, life is not so stable that when there are two options, it's always one of the two which happens.
No, well, the guys have done like 50 years of research trying to frame better the questions and take the people, explain them what is it about, because you can tell actually you don't have to be very creative, just make your decision in base of what you are being told, you know. This has been tested, like these type of things have been applied in experiments, but in a way what you say always end up happening. Because if you want to explain rationally why people made this type of decision, it's because they must have something else in mind. Unconsciously or consciously, as you said. I guess that unconsciously is the only option because the conscious part has been already controlled in experiments, and this still happened. So what remained there is that the only thing you can say is that, well, the rational analytic representational framework it's not going to explain this type of things. You need something else.
Well, actually, it is rational. In a disjunction, it's always you can have an infinite of other disjunction. That's always true. Also, it remains true.
Yeah.
Yes.
A or B or C or
yeah.
B. But also this the Ellsberg and Machina paradox is sort of coherent with the borderline contradiction because the decision is also not decision. It's not a logical, what we hold in mind is not a logical proposition, but something which is, I am leaning towards buying the property, but also there is a possibility that I will not. So it's coherent, it's not...
So that's, I should have made a little graph to show how this, because all these things are explained by the same principle, which is representing, I will mention it in a second. An entanglement of concept combinations is a more technical thing. Entanglement is a truly quantum physical property that you cannot find in classical systems. Well, IRTs have proven certain experiments that show entanglement for macroscopic systems, but people don't agree. It's because it's sort of like a...
Is that the experiment
with the vessels of water? Yeah. But it's a sort of a construction that is legally okay, but it's not exactly what you're looking for. But yeah, but it's a fun.
Yes, there is also a point in his work that it's like comparing classical physics with quantum physics, while the connecting link is a mathematical representation.
Yeah.
And if you go from there, you don't find really a problem in.
Yes. Yeah. That's.
So it's the way it's presented, which evokes this contradiction or incompatibility.
Yeah, there are nice stories about that experiment, but it has been found for concepts, basically for categories as well. I was thinking of presenting the example here, but just to present all the how entanglement can be measured and why the concept, it will take too long, so I'll just leave it for, if you want, I can explain it in another time. So, okay, so this is the idea of quantum cognition and how it deviates from more like classical perspectives. So entities, which here are concepts or decisions or ideas or all these like cognitive entities, let's call it. I don't want to marry with any term. Let's just call it entities, because they can be quantum particles as well. So things exist in states rather than being containers of instantiations. In the same way, like this being a container of instantiation is in a way like having an urn with balls. The instantiation of what you want are the balls in the urn. So here is completely different. You have states. Entities are observed in a particular state, usually observation dependent. So this you introduce the measurement bias, and these assumptions lead to the introduction of collapse. So measurement induces a collapse, a change of state, and that's how you get the observer effect. and the possible non-symmetry, because if you measure in one order, then you have a chain of collapses, and if you measure in different order, so first measurement and then second is a sequence of collapses, but second measurement and first measurement is a different sequence of collapses.
Non-commutativity.
Yeah, non-symmetry or of the commutator. Yeah, and this already gives you non-classical probability, because classical probability in general is symmetric. And next, assuming that entities can be combined and the states of combined entities can be different to the product states of the former entities' states. So the combination of two systems, you have a system in a certain state, and you have another system in another state. When you combine the states, the state that represents the combination is not necessarily represented as a combination of the states. There can be another state that, of course, you will algebraically be able to construct, but cannot reduce to the other states. This is how you get entanglement effects. And well, that's what happened with quantum systems. And interference as well. Interference and entanglement. And then that's the idea for all this combination problem, or like Machina paradox and all that, is that you have your decision, but when you put the decisions together, or the situations together, you have a superposition, and then you can have certain interference between this, and the interference is the one that can give rise to non-classical effects. I will show more in detail the example. And now I'm gonna just, I think I have two more ideas to explain here. One is the two modes of reasoning about conjunction. So now we consider this following situation. You have to estimate the membership weight of the exemplar banana with respect to the concepts fruit, vegetable, and their conjunction fruit and vegetable. So this is where we are going to explain a little bit more in depth why this average was given in the data before, and why you have overextension, and why you have all this. So two kinds of reasoning can be identified with respect to the conjunction. Okay, with respect to the single concept, I say banana for fruit, okay, certain value, banana for vegetable, certain value. But when I get banana for fruit and vegetable combined, two kinds of reasoning can apply. You can think of banana being an exemplar of the fruit, of the concept fruit and vegetable as a whole thing together, whole concept fruit and vegetable. Or you can think of banana being an exemplar of the concept fruit and of the concept vegetable separately, and then make the combination using the connective and. This second part is, of course, what logically you will do. You will estimate the typicality or the membership weight or whatever with respect to fruit and vegetable by separating, by decomposing the concept into its components, fruit and vegetable. But there is a first, I put first, but it's secondary if you put it in a historical perspective, that banana is an exemplar of the whole concept, fruit and vegetable. And this whole concept not necessarily can be reduced to fruit and vegetable. It's something else. Whatever you want to call it is just something else. So in the first case, a single instance of banana is taken into consideration, and the membership is estimated with respect to the meaning of a single concept, which is the combination. While in the second case, you take two instances of banana in mind, and you measure one with respect to fruit and the other with respect to vegetable. So this is a picture of how these two reasoning modes occur. This is what we call, when you consider the whole concept, if you see the quotes are between the whole sentence, fruit and vegetable, you have one instance in your mind and you estimate yes or no. This is modeled in our, I won't give much of the details, this is modeled in a Hilbert space. And the logical mode of thought, well, you have two exemplars of banana, one applied to fruits and the other applies to vegetable, and then you have a logical table here, truth table, and you estimate the outcome logically. So you get yes, no, then yes, no means no, and here yes, no, just give yes, because it's an emergent mode of thought where the concept, the combined concept has a new meaning that is not necessarily decomposed in the logical structure. And that's where you get all the averages and all that stuff, because the formula actually is approximate. First term is an average. and the second term is interference. But I'll show this in a little.
There could be also some if you go back to the slide, on the second example, there could be some biases. If someone has a yes/no,
and still say yes.
And still say yes, because it's ambiguous. They will not necessarily think logically about how to deduce the phenomenon. So.
Well, these cases we are trying to reduce to this. I know you can find there is a logical function and like a utility function that tells you that okay, if I have a very high likelihood for one, then I don't care about the other. But that's still not logical, because the and has a pretty concrete meaning in any logic, and then you can go to the details, but this framework basically is doing the work, and that's why of course you can put alternative frameworks, but you have to give a cognitive explanation, and then you have to be able to represent the experimental cases and so on. And this normally, when you put this type of things, you get to many parameters. Like there is I think one guy, Nosovsky, he proposed a model of that kind using similarity measures and so on, but then the model has like millions of parameters that have you cannot ever test. While this model is more like just two concrete modes of reasoning, of course it's based upon certain, and the good thing is that the first term of this model gives a very good approximation of what happens in general. So this is just like a mathematical short description. I don't really want to go here, but the idea is Fock space of quantum mechanics is a mathematical tool to represent systems where you have many particles, and since we have only two modes of thought, we only use the case that there are two types of cases: the case when you have one particle and the case when you have two particles. So this is basically the number of bananas in your reasoning process. One banana in your reasoning process, two bananas in your reasoning process. And one occurs in an emergent way, like with the Hilbert space, as I said before, formula, which is here, and the other occurs in a logical way. So I'm gonna show very shortly what is the meaning of this. So AB is the state of the combined concept, A is the state of the first concept, and B is the second. So AB is fruit and vegetable, considering the two modes of thought together as a superposition, because that's what this quantum model does. We say there is a superposition of modes of thought. The first mode of thought is non-logical and assumes that the concept it's created as a combined concept is an emergent entity, and is represented by the addition of the two concepts. You have a vector representing your first concept, you have a vector representing your second concept, and then you take the average of these vectors. It's not really the average, but it's the normalized sum. And this is what represents the emergent concept combination.
What is phi?
It's a phase.
Phase?
It's just the phase of the vector. Yeah.
And n is what?
N is the weight of the mode of thought. So how important is the first mode of thought in this reasoning process? And then 1 minus n squared, because these vectors have to be normalized. And then C is a probabilistic representation in a classical way. So this vector, you can manage to create a vector in this space that is always going to represent any logical reasoning process. That's basically what you can prove. I won't elaborate on that. But the idea is that you have certain percentage of your mind is in a, you can say that this is the unconscious state or the emergent state, and this is the logical part of the reasoning. So, and we assume that there is a superposition of these two things, and that the outcomes of your experiments will reveal what type of reasoning is dominant in the process.
It's interesting because when you say banana, it's as if predefined, but actually the banana itself is defined by the categories that you assign to
Yes.
it. So there is a kind of, not a feedback, but reflexivity between the two.
Yeah, that's the thing that, again, you cannot put things as containers of instantiations. Banana is not just like a probability of being this. It depends on many, how you present, and if you put banana as a fruit and vegetable, this is going to affect the state. So that's where you get the non-commutativity effects or observer effects in general. So this is the mathematical model, and the formula looks more or less like this. The formula for the typicality, or no, the membership weight, we said. The membership weight of banana is going to be given by n squared, which is how important is your mode of thought in the emergent mode of thought. The average between how much the banana is fruit and how much is a vegetable, plus an interference effect. So that's why when you only consider the emergent mode of thought that I was saying, the first part, you get that the average is the first term and the interference is the second term. This interference can be bound. You can bound the interference by certain formula. So in many cases, this interference is very small. And actually, when any of these two guys, mu A or mu B, is large, then this interference is very small. Interference can become large only in the case that these two values are pretty much close to 0.5, which is when you don't know. And that's the interesting, the beautiful thing, in my opinion, is that when you don't know about the membership weights, is when the interference can occur more. You can have a lot of interference when you don't know, but when you do know something, either you know it is not or you know it is, then interference disappears. So logical thinking, in a way, destroys the possibility of interference, while not knowing, uncertainty, is what brings and fosters the interference, which is another type of mechanism to create to reason, to create estimations of the meaning of things, which is based on coherence, and then that connects to like other things that I won't talk today, and I don't even know that well. But the thing is that this equation here establishes quantum-inspired conditions of possible experience for the membership measurement. So it's a new condition in the same way that you can get inequalities and polytopes. This is just another framework or another alternative for the conditions of possible experience, just quantum-inspired. The idea is, can we test if these new conditions of possible experience apply? And that's what we did within it's a psychological experiment by Sandro, Soso, and us. We tested these conditions, and we did it for, given this example, the exemplar tomato, fruit, vegetable, but now we consider fruit, not fruit, vegetable, not vegetable, fruit and vegetable, fruit and not vegetable, not vegetable, fruit, non-fruit and non-vegetable. So all the possible logical conjunctions and negations. If you analyze the conditions of possible experience for this case, you get that these equalities have to follow. So tomato, this is minus, I'm sorry, this is minus. All these are minus. So the thing is that the membership of tomato has to be equal to the membership of tomato and vegetable plus tomato and not vegetable. Because these are two possibilities. You are either a vegetable or not vegetable. So, and it's like the Elber's paradox again, it's the same. This is called marginal probability law. So if you put a new variable that has two possibilities, then the probability of your first event has to be equal to the sum of the probability of the first and second event in one case plus the first and second event in the other case. Because this is like, these are all the possibilities. So then this has to follow for the four, and this is just that the sum of all the probabilities has to be 1. Okay, so these are the conditions, and this is what the data shows. This is what you should find for the data if the conditions of possible experience for this experiment would have been followed. You need 0 for these measurements that we did, and which are actually these values here. Mu A, mu B, minus, these are minus, sorry. Everything has to be 0 here, all these indicators. And what we found is that the data actually spreads around the value 0.4, between 0.3 and 0.5. So the deviation from classicality, in a 95% confidence, it's gonna fall within these points. This is because I tested for many concepts, so all these points represent different concepts. And the one point represents the one extreme of the interval, and the other point represents the other extreme of the interval. So you have 8 points for each color, because you have 4 concepts, 2 ends for each concept. So anyways, in red you find negated concepts, and in blue you find non-negated concepts. So it seems that the non-negated concepts concentrate better. Well, these are more things you can say. But the bool conditions of possible experience are violated in a pretty stable way, because actually, if you look at the possible values that these intervals can assume, is between -1 and 1. It's an interval of length 2. So if data is random, you will find everything spread between -1 and 1. If data will be classical, you will find all the points concentrated around 0. 95% confidence tells you that the values fall within a band of length 0.2, which is 10% of the full interval. So that is giving you an indication that the data is pretty much concentrating 95% of the times in the same place. So this is a very strong indication that the conditions of possible experience developed for this case are not held and are actually violated in a very stable way. If we analyze these violations with respect to our model, we find that the value 0.7 is critical, is a critical value. Below that you cannot model this, and above that you can. So you need at least 70% emergent thinking or unconscious thinking, or the first reasoning mode, the one banana reasoning mode, has to be 70% dominant in order to reproduce these patterns. So this is actually saying that non-logical reasoning is more dominant in general, at least on this experiment.
This is something about the minds of the people that are contributing to this experiment.
Yeah. And I did another analysis for my thesis and found that this condition, analyzing other experiments, is the same. Like, you can always, or not always, but for all the experiments that I have analyzed, this condition is always achieving the possibility to represent the data. Another condition, some cases you have more, not just this condition, but maybe n larger than 0, between 0.4 and 0.6 also performs well, but not in another. And so this seems to be the only stable case that fits all the data in experiments of this kind.
So you need actually a lot of uncertainty or not knowing in order to have some kind of creative outcome from this.
Yeah.
Interesting. It's well above 0.5.
Yeah. If it would be 0.5, means you're half and half, like half logical and
yes,
and
but here
this, no.
a little bit.
It's more.
Quite a bit more than this, in order to have some kind of a creative, non-conventional way of analyzing.
And it's proving that this is our reasoning mode in general. We are not in a logical state of mind, almost, unless we are doing math maybe. But normal people, normal cognitive activities, their state of mind is far from logic, and is more, according to our model, is more in an emergent state where coherence play more an important role, and averages play a role too. Okay, so the model having two fundamentally different modes of thought accommodate to the data. So are the new conditions of possible experience? Yeah, I'm just gonna define here, like, probability estimation, as you say, membership, typicality, similarity. All these, in my view, are called semantic estimations. I just call them semantic estimations as a general concept. And the idea is that, given a semantic estimation, do the concepts involved in the semantic estimation affect the mode of thought? That's the point. Do we reason more logically about certain concepts than about other types of concepts? And that was the question that I pursued. And this is the last idea. How long have we been already, Victoras? It's more than an hour?
It's more than an hour. But
okay. Well, I only need like 5 to 10 more minutes to explain this. And So I'm going to try to go back to the foundations of probability again and explain different modes of thought, like propose a sort of categorizations of modes of thought in terms of the level of abstraction of the concepts you think about. That's basically what I will try to explain. So levels of abstraction and possible experience. It is well known in concepts that in human language and memory are organized in hierarchies, at least natural concepts. So natural concepts means things we can like touch and like observe, experience in a physical way. So for example, you have mammal, dog, puppy, and then you can organize in a semantic graph. Before mammal, maybe you will have animal, before animal you will have living being, and before you have thing, and then from puppy you have a little puppy, and like you have my own pet, or the pet of my neighbor, you know, instantiations of, so you have a sort of hierarchy where you can put all the things you can think about, not everything, but at least something that can be correlated to physical stuff. At the last level, which I put on this to the right, you encounter physical realizations, which are space-time events in your experience. This puppy you see, like this thing or whatever. And higher levels are semantic abstractions of lower levels. So you collect all these experiences and put in one thing, and then all these more abstract experiences you put in another level, and that's how you can hierarchize.
I just wanted to ask, is this the same basic idea that was put forward in Kurzweil's book, How to Build a Mind? Because he talks about the conceptual hierarchy.
Yes.
It's a very old idea.
It's a well-known result obtained in psychology. Actually, I will make a little interlude to connect to this. If you think of this graph, then the question that was studied in the 70s is, where do we think in general? At what part of this graph is where our mind is normally thinking of? Okay, so you might have, let's take these three levels, mammal, dog, and puppy, and then the experiments made by this famous cognitive psychology known Eleanor Roche. Yeah, she discovered that the intermediate level between very abstract and very concrete is the place where we first learn words, is the place where we easily remember, and is also the place where most literature is pointed to. So this word is many more times written in a book than this word or than that word. This word is easily or first memorized or learned by childs than that one and that one. And like everything you want to say, where what will indicate, what will make a difference in what is more frequent in our reality, in our cognitive states, this intermediate state is where we normally stay, where we communicate, where we just tell a story to your friend. All your concepts are going to be like within a certain intermediate level. Just when you want to make some details, you go here, and when you want to make abstractions, you go there. But normally, there is a sort of like reference point, you know, abstraction level reference point for our reasoning, and we have an infinite hierarchy down and an infinite hierarchy up. So this is a pretty interesting result. Okay, so it's now very clear that there are abstractions, and so what you can say is at the physical level, at the last level of space-time events, which is where physics can be concerned, the conditions of possible experience must be satisfied, at least in the macroscopic realm. If you go to quantum reality, yeah, that is not physical for us, it's more like lab kind of thing, but at least from a classical scientific perspective, the conditions of possible experience have to be satisfied in the stories we think, in our memories or in our constructions about the physical realm, which is the lower level. Then hypotheses, more abstract levels, however, do not necessarily satisfy these conditions. And my hypothesis is that quantum-like conditions instead. So the idea is that the higher you go on the hierarchy, the less classical your thought is going to be, and eventually more quantum.
Not necessarily. I think that the highest level of abstraction, well, some levels of abstraction like mammal, I think are more classical than levels of abstraction like puppy.
Yeah, I go to that in the end, but this is just a first approximation hypothesis. There is a refinement to that idea, but I have data for this hypothesis, not for the more refined, which I'm still collecting. So how do we test this? Let's go back to the urns and balls, and I will mention the feature of indistinguishability. It's a statistical notion. So when you can distinguish events, you have a certain type of distribution. If the particles, for example, in a certain urn are undistinguishable, you extract particles and you know they are distinguishable, then you can measure stuff about them like color or wooden, and you can then collect and make count cases, establish frequencies, and then you can obtain a distribution from your measurement process. When the particles are distinguishable, this I think I cannot elaborate to go further. When the particles are distinguishable, you get Boltzmann statistics, which is described by this function. When you have quantum particles, then you cannot distinguish among them, because if you perform a permutation, you cannot know what happened, because these are waves. Because it's a wave function, there is a way to explain very concrete, but I don't want to elaborate on that neither. So then you have that quantum particles are indistinguishable, and this gives rise to a completely different distribution. Here you have a more exponential, here you have a linear one. Okay? And then my question is, let's elicit concepts. Not take particles from a certain experiment, but think about elicit a certain number of an amount of concepts, and then see how they distribute. If they distribute like distinguishable particles, then we will say there is something classical here. They behave like classical distinguishable objects described by classical probability. If they behave like quantum objects, or like non-classical at least, we might consider the quantum distribution and the feature of indistinguishability of concepts of interest. And we take concrete concepts, as we were saying, human or mammal or something, and then make elicitation, or abstract concepts. So your concept of mood, you be sad or happy. So this is completely different. Concrete, human, man or woman, abstract, mood, sad or happy. So these are the two dimensions, more or less, like the abstraction level is where we were playing. So what we say is give a concept like this, 9 humans, and then I give you instantiations of these 9 humans. So 9 men and 0 women, 8 men and 1 woman, and so on and so on, 0 men and 11 women. And then I give you another abstract concept like 11 moods. Okay, you can be 11 sad and 0 happy, and so on and so on. So the idea is to say, you have to choose what is the option that you think is more representative or more likely for you concerning this concept. To many people, like 100 people, and then we make the statistics of this. I don't remember, maybe 87 participants, near 100. And this is what you get. We did some statistical comparisons using like pretty standard statistical indicators, delta big, which is an information theoretic measure, and the R square, which is like just the fit of the curve. And of course we found what is the best probability, because you can say, okay, man has a certain likelihood, woman has a certain likelihood, probability to be elicited. They are not necessarily 0.5, 0.5, it can be any number. You can have a higher tendency to choose men. Your population can have a higher tendency to choose men or woman, one of the two, but the two probabilities have to add to 1, because these are the only 2 options. So what I found was, for the 2 possible distributions, the best probability value that gives the probability that gives the best fit for the 2 types of distributions with this parameter set. So, for example, and as I said, the quantum distribution, which is the Bose-Einstein distribution, looks linear as a linear function, and the Boltzmann distribution looks like similar to the Gaussian distribution. It's not the same, but looks like a Gaussian distribution. This is discretized, that's why it looks not really beautiful. But for different parameters, as you see, it looks different. So what we found was the parameter that provides the best fit, and compare for the 2 types of distributions what gives a better representation. And we found that the more basically, the result is not as strict as I'm saying, but basically, the more concrete the concept is, the more you find that the Boltzmann distribution, the classical particle distribution, fits the data. When you go to more abstract concepts, you find that the Bose-Einstein distribution, the quantum distribution, provides a much better fit of the data. This is saying, in other words, so I give the example, 9 humans is a very good fit by the Boltzmann distribution, while the Bose-Einstein distribution gives a pretty bad fit. When you go to 7 expressions of affection, which is in between physical and emotional, you get that both distributions give a decent fit, but none of them can be really discerned what is better. You find this distribution is kind of like that, but it can also be kind of linear. It's like just, you cannot decide. While when you go to something more abstract like moods, you find that the linear distribution performs better than the Boltzmann distribution. We made it for more experiments, and we actually tested on the web as well, doing like a computational experiment using a search engine. All these things, the states, how many web pages mention these states, and again you find the same. For more abstract concepts, you find the distribution is more linear, while for less abstract concepts, you find that the distribution is more like Boltzmann, and also changes with the number. When you stick to
what were the participants exactly supposed to do?
They were requested to choose among these options.
And choose on what criteria?
They choose their criteria. What they decide for them to be a better representation of this concept right now.
Okay.
We didn't know how to frame it better at the moment. Now I have a better way to do it. But it's interesting that you find the same on the web. And another interesting thing we found is that for small numbers, like between 0 or 3, let's say between 3 and 8, the distribution looks pretty much like Boltzmann. But when you go to larger numbers, like 10 or 12, there is a shift. A same concept. You say, for example, Republicans and Democrats, for just to give 2 possible things. And you test on the web, 5 Republicans and 6 Democrats, or 4 Republicans and 3 Democrats. You count all this, you get the matrix, and then you build up these distributions. And when you consider small total number, like 8, the sum of the things have to be 8, for example, you find that everything behaves like Boltzmann. When you go to larger numbers, everything behaves more like Bose-Einstein. So the idea that we connect to this, nothing like really concrete to say, but it's related to the way in memory we are able to grasp, or we are able to memorize or count or reason about 7 things simultaneously, numbers or whatever entities we can keep in mind as distinguishable. And that's why they give rise to Boltzmann distribution. When you have larger numbers, you cannot keep them in mind as distinguishable entities. You need to put them in another way, which is more abstract, and is represented by indistinguishability. If I tell you, think of 100 animals, are you going to have a distinction between these 100 animals in your mind? Probably not. You're just going to have something that represents 100 animals in your mind. And then, depending on the reasoning process, you will go more to distinguishable, treat them more like distinguishable entities depending on your reasoning. If you keep your 100 entities in mind in an indistinguishable setting, you cannot apply logic to it. You cannot disentangle them because you cannot distinguish them. You cannot apply logical rules or reasoning in general. So this is more or less the result. And so the hypothesis that concepts are more abstract or concrete in human mind can be refined identifying 3 domains of semantic experience. This is the point you were mentioning. I just put these 3 domains. One is personal experiences. So only perceived experiences apply, what have happened to you in your lifespan, in your life. These experiences are sparse because you haven't experienced everything. You just experience one thing of a certain kind. So this is going to be sparse in a distribution. If I ask you, probably you have experienced 3 cats and 5 dogs, but haven't experienced 4 cats and 4 dogs, because it's just your life. Your aunt has like 4 cats and 6 dogs, but not 5 and 5 or whatever. So you cannot build up the distribution in according to your personal experiences only, but because it's your personal experiences, they should behave like distinguishable entities in average. Then it comes the worldview. So it's not only your perceived experiences, but also the ideas you assume to apply in other people's experiences. This will be classical, I assume, because these are all the possible experiences we can have in our minds about the world. And the other is the realm of imagination, where you can find any possible reality structure. And this, I assume, is non-classical, and eventually, some cases, can behave more like quantum, where just as you were saying before, Clement, you can always make something up with your mind. So we can test a similar situation to the previous experiment, inducing this type of thinking, explaining to the participants, think and try to think of this way. And this is the type of data we collect. So I did 3 experiments, or two cases. Throw 6 dice. The result of throwing 6 dice. Of course, someone who knows probability will find that there is something like intermediate values have higher likelihood and extreme values have lower likelihood. According to this person, seems to never have thrown 6 dice in his or her life, but he or she knows that they will distribute this way. While when you can just imagine the possible outcome, everything can happen. And another concept is 5 animals, and then you say dragons and unicorns and this description you have never experienced. You know that nobody's going to experience, but then you find that this is completely logical. It's not logical, but reasonable from an imagination-like perspective. This distribution looks like, if you plot it, is more like this, and this distribution is flat like this. These values 0 to 7 are an estimation of likelihood. So 7 is a lot, and 0 is no way. Okay. So this is a small indication that you can continue analyzing different types of reasoning and separate not just in terms of the abstraction of the categories or concepts you work with, but also with the type of reasoning in a sort of context of reasoning. And the conditions of possible experience of logics probably are profoundly related to cognitive science, but we show strong evidence for the non-satisfaction of these conditions in cognitive phenomena, and also have proven that quantum-inspired models can propose an alternative to this type of situations where the classical conditions don't hold, and also you can introduce modes of thought, and so on and so on. So this is more like the summary. Conditions of possible experience don't really hold in nature, in cognitive nature, and quantum cognition can provide a sort of alternative.
Could you for a second go back to the screen with imagination?
This one?
Yeah, I wanted to write down what you were saying there. I didn't have a chance.
Yeah, this I just deleted today because I had another explanation here, but I read it again and I didn't like it. So because I'm changing a little bit my mind about how to perform these experiments. The thing is, just as a last word, when we reason, we are in a certain reasoning context that is given by the situations we are at, and it's very hard to define, but certainly the reasoning mode we have induced by the context at which we are is influenced by things, it is in a certain way non-logical. That's what I'm trying to say. That's why, and I think, for example, kids don't have any logical structure at all. They just reason, and now if you say it's going to come a dragon into this room, they will believe that. It's possible for them. It's a possible experience. And we somehow shape our minds to don't believe on these things and to don't imagine, because the reality has a certain structure. But that's not ever going to be the end of our mind. And that's why logic, in a way, has to be overcome by new theories.
I just want to say that there's a really nice example you just gave of the child's mind, and it reminded me of, I was reading a book on psychedelic experiences in Latin America, and in the ritual ceremonies where they introduce the psychedelics to children, the children are not surprised at the experiences they have. They're just like, my mind's transcendental. Like, it's not a surprise.
Yeah, no, it's And also, well, schizophrenic people also have this type of behavior or reasoning that is just not, it doesn't, is in a way, I don't know really about that, I'm not a psychiatrist or psychologist, but I have seen some stuff, and it's just like the incapacity to differentiate what is the reality, what is this, to what is this,
But also,
you know,
and
and that's what
between
makes us
the realm
normal.
of the creative people, they sit between the realm of
Yeah, if you want to be creative, you have to be able to shift
Yeah.
to this type of reasoning. If you stick to this, you won't be that creative, or yeah, well, it depends. So this is all what we have, personal experiences. That's what we have. This is what we create to represent the world, and this is what we need to be creative, basically. These are the three huge stages, and I think there is a whole bunch of different possible characterizations, and you can discover conditions of possible experiences around these things as well, because the conditions of possible experience developed by Bull apply for this thing in the classical physical world, and that's all. It shouldn't be taken to cognition, and it certainly didn't work when you apply it to quantum physics. So not even in the physical realm, space-time realm, it's working. So yeah, well, thank you.
Well, I think the basic problem is always the same. The classical mode of thinking, logic, rule, etc., starts by making distinctions and assumes that things stay in all those distinct things. So balls in the earth, the balls belong to particular categories, the balls are identifiable, are distinct, they don't mix. Well, what you have in reality is that things interact and together form things that are more than the sum of the parts. You have emergence, as you said, and that's also how our cognition works.
Yes.
Our cognition does not start by accumulating experience as discrete little balls in our brain and then select some of those balls out. No, what our brain does, it aggregates these experiences and builds something out of it that's more than the sum of the experiences.
Yes.
And that is what you call the worldview, but it's also the imagination, because it goes beyond more just making a system out of it. It's a kind of a fluid amalgamation of the experiences that has certain properties that are not in the individual experiences, that fill in gaps. And that's part of what's called the constructivist view of cognition, that is that most of the knowledge we have in our brain does not come from perception, from things that were put into our mind, from experiences, but from constructing a coherency out of all these discrete bits. So what the brain tries to do is to try to make a coherent gestalt out of it, but it does not work with discrete entities. And the whole point that you speak about, the classical point of view, starts by having discrete entities in discrete categories, all distinctions that are kind of invariant. And that's not how the world functions. It's certainly not how the brain functions.
Yeah, just to add a little comment to what you were saying, because it's the notion of coherence. It's a notion that is not. I mean, it makes sense. It is a coherent notion, but it doesn't. I don't know any. I've been asking around, and there is not many mathematical frameworks to describe coherence, except in the realm of waves, wave functions, and that's why the quantum framework is also. It's another reason why it could work. Because if you look at the formula to represent the state, you get this. This is basically the formula, okay? And you have this thing, the square root, I'm reducing the function here, but here what you have is the possibility to define coherence. Because how in a short, because the state A has a certain phase. You give a phase to the state. It's not represented explicitly here, but it's represented explicitly here. So there is a phase here, but A itself has its own phase as well. B has its own phase. And when you put them together in this operation, these phases add. And this can create interference. And coherence is just, well, from a wave perspective, coherence is the right matching of phases in a certain way, like depending if you want to create or destroy or whatever. But the coherence process is to keep these phases playing a role in the process.
Mm-hmm.
So that's why also, this is an indication, it's speculative, but that's why the representation of cognitive entities using state vectors, like in quantum mechanics, could give rise to a formal definition of coherence, which in other languages I couldn't find.
But now I've given my criticism of classical logic, now my criticism of the quantum approach, which is that the quantum approach still assumes that there is a state, a static state, or what really happens in reality and also in the brain is that it is a dynamic process. Things are constantly changing. There is not a single state. It's like a chemical organization. It's something that looks stable from the outside, but where constantly things are changing on the inside.
Yeah, no.
And in our brain, there are no things like stable categories. There are patterns of activation that are circulating to circuits of neurons, and sometimes these patterns of activation collapse in a particular interpretation, but the next moment they are somewhere completely different and look completely different. You have the stream of consciousness which is constantly changing shape, and from time to time when you need to make a decision, for example, or you need to recognize is that a cat or a dog, it collapses temporarily into a particular category, but the next moment it's already going away from that category. It's already starting to explore new emergent, possibly emergent interpretations.
Yeah.
And that's something that the quantum formalism cannot deal with.
It can. It's not doing it now, but it can. The problem is that you need a more complex you need a sort of Schrödinger equation for it.
I don't think a Schrödinger equation can do that, because a Schrödinger equation is essentially a deterministic linear equation. It's a self-organizing process, which means we have all kinds of feedbacks in there, which is Schrödinger equation does not deal with.
Yeah, no, but like the Schrödinger equation, what I mean is that you need a dynamic, first you need more than one concept. You need to model a worldview, basically. To do what you want, you need many concepts. We are just doing like very toy models for one concept. So I know, but I don't think that this is something that cannot be done. I just think that it's something that completely different nature. But eventually the same framework can be applied. I don't know how to do it personally. I don't know how to apply this and extend this idea.
Trouble you are struggling with the mathematics for this extremely simple case. If you try to extend that same mathematics to this dynamic case, I can promise you that
the problem in the quantum kind of Schrödinger equation is not in the equation itself that can be deterministic, but the boundary conditions and the initial conditions. It's like in classical physics. When you have a limited number of particles, you can have the Hamiltonian, and you can determine everything. But if you go to infinite number of particles or very large number of particles, you have to start to apply statistical methods, because you don't have a specific, you cannot formulate a specific initial conditions in order to solve the deterministic equation. So this goes to the work of Prigozhin that was treating this. I have another comment about the whole thing. Is I understand that from a scientific point of view, you focus on the on the cognitive aspect, and you perform certain experiments, while there is an implicit assumption that reality is predetermined to any cognitive process, but actually what we call reality is a kind of reflexive process. So this whole approach can be applied to not only to the brain or to cognitive processes, but to all reality. And I'm investigating what is called the theory of individuation. And in theory of individuation, what we call knowledge and categories and the actual state of affairs of a certain reality, they co-determine each other. So it's not only that our cognition is capable of making a certain distinction at a certain situation, and not capable of making the distinction another, but the distinction themselves do not exist, and we create them by the observation, and this is why the whole system of mind, reality, actually it's a reflexive system. You don't have an initial point and then you cognize what is happening.
Yeah.
And this is kind of supplementary to what Francis said, because it's a completely it's like when I said before, when you have a banana, what is a banana? Banana, you look at it, it's a certain construction of data that you see with colors and shapes, etc. But we form it, and evolution, of course, made certain concepts very stable and other concepts not very stable. And this is the distinction between imagination and actuality. But the mind and the world are not bound by this.
Yeah.
You can go much farther with the same.
We have
the same ideas.
Maybe to give like a conclusion line, because this is the more speculative thing that I'm not mentioning here. It connects to the notion of experiencing something or having something, and now we have the web, which is a sort of collapsed state of multiple things that are stored there, available for observation permanently. So the thing is that when we pronounce a word, when we say something, when I'm communicating now certain ideas, but I'm not really like sharing completely my ideas, because I have to express them only. So what you are receiving from what I'm saying is not what I think, it's just what I say about what I think, and I'm trying to communicate. So you are receiving collapsed states of my concepts, and you are trying to reconstruct the concepts I have in my mind by the words I have. And your reconstruction process works with your own worldview, with your own tools. You have your own tools to do this construction process, and then when you talk back to me, I assume you have constructed this and that, and this is how communication works. So in science there is something called inverse problem, which is used in tomography and things like that, which is to indirectly obtain measurements from a system. So you want to observe a certain property, but you don't have access to that thing. For example, if you want to measure the density of the Earth in a certain spot, you cannot measure the density, but you can measure the gravitational field above. And then from this gravitational field, you know the relationship between the gravitational field and the density and the distance, and then you can perform an external measurement. So communication, in a way, applies to the same process. We are only able to exchange collapse states, and we internally make this deconstruction process, and this fits perfectly well. I'm not sure if perfectly, but it fits pretty well with the way that inverse problems are applied in quantum physics as well. So I don't know if this connects. I think it connects to what you were saying in a certain way, but this is very speculative.
This is very important.
Scattering, you know. We are doing conceptual scattering, and the collapse states are words, basically, and I can hit you with my words, and then I see what comes out. It's like scattering.
I think that's a very correct idea. What you're doing is you start to put in the language of cognitive science, you start from a sub-symbolic level of neural activation, which you then collapse to a symbolic level of words, which are discrete entities chosen from a finite vocabulary, which then come into my mind, where I kind of decollapse them into the meanings that you might have wanted to express, but which probably will not be the same, because my mind is not organized exactly the same way as yours. Insofar that we have had similar experiences in the past and some degree of similarity in the anatomy of our brain, I will understand you. But in other aspects, my experiences, I will have different associations with the same words than you, and I will make different connections, and I will see different connections than what you do. That's why it's difficult to communicate about these things. But it's possible. But I think that the moral of the story is that because we are constantly doing that, collapsing these very complex inner states into discrete symbols, people tend to think that those discrete symbols are the reality.
Yeah.
Yeah, but
And they
first-
forget that they're an extremely simplified, caricatural version of reality.
Yeah.
And therefore they are making all kind of the most complicated theories about these symbols, or they're speaking about kind of ghosts almost.
But Francis, I have a speculative question. What if we take out the human observer and we look at the world, at the universe without human observers? I think the same.
We can't look.
No, just as a, no, it's speculative. It's a thought experiment. I think that everything that Thomas said here still applies to the interactions between things.
Yeah.
So
Yeah, for me
it
that
is
is
something
more-
which is immanent in the very state of affairs of the universe. It does not have to do specifically with minds. With minds, we want to make experiments, and you want to prove a certain point,
Yeah.
you make a PhD, etc. But this is something which is immanent in the very state of affairs of the universe.
Yeah.
These things are not defined. They are defined by interacting with each other.
Yep, exactly.
That's
The meaning arises out
Yeah.
of the connections and interactions.
so it
It's
goes
not.
much.
It's not. It's always the Newtonian view is the billiard balls. Reality
Yeah.
consists out of small, discrete, separate, objective things, and those things from time to time bump against each other. But that's about all the interaction they have. They remain autonomous, discrete, separate, distinguishable, etc. While in reality, everything interacts with each other and changes itself while interacting, and new things emerge. And that interaction is ongoing everywhere.
You
And-
should.
Our mind is part of it. Of course, we cannot do without observers. But I wanted to make the point that it's not observer independent in the sense that that is implied by the way that this research is being done. It can go much farther than this.
I'm gonna
Philosophical.
share a paper with you where this idea, the idea you are just explaining, it's connected to this. Like it's explaining the behavior of quantum particles as if they were conceptual entities. It's another interpretation of quantum mechanics, thinking that the way that quantum particles interact is the same way than the way the concepts interact in our minds. So this is just like a more, and then concepts are the ultimate entities, and this is where all the coherence and all the stuff happen. It's a 2009 article written by Arts in Foundations of Science, I think. So yeah, it's a very nice article. To me, at the same level of this other, which is a top thing for me.
But that's one half of the argument I always make. Reality is a very complex network of interactions out of which constantly new things emerge. But the symbolic level, which reduces this complicated mess to a number of discrete entities, that reductionist approach can work because within this network of interactions there is a tendency to stabilization of autonomous systems. And that's what, for example, chemical organization theory does. It shows you how out of a network of reactions you can have organizations that are self-maintaining. Human beings, animals are self-maintaining, atoms are self-maintaining, molecules are self-maintaining. So at different levels you have self-maintaining entities. But you have to remember that these self-maintaining entities are made out of these processes, and sooner or later these processes will escape and create something new. And that's what happens in the mind typically, because our brain is very flexible. It constantly tries to get a better view of reality, which means it's constantly constructing, making better constructions, and reducing that to the laws of formal logic. That's a mistake. It does not mean that the laws of formal logic are not useful. They are useful if you stick to these separable, independent entities, more or less like the balls in the urn, then it works. Just don't assume that the whole of reality is like that.
That's the
reality will
basic
always
point.
bleed beyond the categories that we impose on it.
I think more questions.
Can you send the
Slides? Yeah, of course. Yeah. Slides, and I can send a few papers also for further reading if anybody is interested, because there are a few papers that are really, I would say, core readings. Not necessarily of arts, a couple of arts.
They might make for a really crazy Friday night.
Yeah, for tonight,
Let's
yes.
not, yeah, we'll not get too crazy.
Okay.
Okay, thank you again.
Yeah.
Thank you.